Hello, everyone, and welcome. I'm recording this in my hotel room in Boston because I can't be there on Monday because I'll be traveling that day. So anyway, thanks for putting up with me. And remember, I'll be available on Tuesday during my office hours time. And then I'll be on Zoom on Wednesday from 1 to 2 to answer any last minute questions you might have. And then also remember that the exam has been moved to Thursday. From 2 to 11, and you can find all that on Canvas, okay? So today we just got a couple of things to finish up from chapter 6, and then a little bit of a review for the exam, all right? So here we go. At the end of last time, if you remember, we were looking at gas stoichiometry, and we looked at a quick problem on how you do stoichiometry for reactions involving gases. And remember, instead of mass to moles to moles to mass, right, we saw that you can go from liters of a gas, right, to moles to whatever, right? And in the example, we used the idea that at STP, right, at STP, 1 mole is equal to 22.4 liters. So that's a good little relationship to keep in the back of your mind, all right? Okay, let's move on to kinetic molecular theory. So kinetic molecular theory is a model for how gases are. Now remember what we've been learning all along in terms of how science progresses. We go from observations to laws, and then the theories, and theories explain how nature is, right? It's a model for how nature is. So we're doing that in this chapter, right? We saw some observations on the properties of gases, right? And then we saw some laws, the simple gas law and the ideal gas law. And now we have a model, and that model is a quantitative model called the kinetic molecular theory, okay? In this model, gases are seen as particles in constant motion, all right, like you see here. And the model has several assumptions. The first one is that the particles are negligibly small. In other words, their size can be ignored, right? So we just think of them as point particles. And the reason we can do that for a gas is because the volume of an atom is so small, right, compared to the space between atoms in the gas phase, that you can ignore the volume of the individual atoms, all right? So the second assumption is that the average kinetic energy of a particle is proportional to the temperature in kelvins, all right? So average kinetic energy proportional to temperature of the gas in kelvins. What that means is that as the temperature goes up, the particles have more and more kinetic energy, all right? And that also means that as the temperature goes up, the particles are on average moving faster, right? So we can just write kinetic energy is proportional to temperature, all right? We can also say that since kinetic energy is 1/2 mv squared, we can say that 1/2 mv squared is proportional to temperature, okay? So notice that at a given temperature, the more massive a gas is, the higher its mass, the slower its average velocity will be, all right? And we'll look at that a little more carefully in a minute. Third assumption is that the collisions of the particles with each other and with the walls are completely elastic. What does that mean? That means that when a collision happens, there's no loss of kinetic energy, all right? So, for example, when two billiard balls collide, like you see here, that would be a pretty elastic collision, right? Because the billiard balls come in with certain kinetic energy and they go out carrying that same amount of kinetic energy. When two lumps of clay collide, that would be an example of an inelastic collision, right? Because the two clumps of clay are basically going to stick together, and a lot of energy is going to be lost to heat, right? So that would be an example of an elastic collision. What we're saying is that for gases, the collisions are largely elastic, okay? So this model is a quantitative model, and it predicts and explains a lot of the things we've seen. So for example, we saw that the volume is inversely proportional to pressure for a gas, right? And why is that? Because as the pressure goes up, right, the collisions with the sides are more, and in order to keep the same temperature, if you're gonna have the same temperature, the pressure is gonna have to go up, right? So volume and pressure are inversely proportional. Volume and temperature are directly proportional, right? Because as the temperature goes up, the particles move faster. In order to keep the same pressure, the volume has to go up, right? So anyway, a lot of the laws that we have already seen, the simple gas laws and the ideal gas law, can all be predicted from this model, all right? And then there's a couple other things that we can get out of this model. And one of them is molecular velocities. So we can actually get, since we know that 1/2 mv squared is proportional to temperature, we can actually get a relationship between the velocity for a molecule at a given temperature. So that equation is this. URMS is equal to the square root of 3 RT over the molar mass, okay? And so what do these things mean? This is the root mean square velocity, all right? The root mean square velocity is sort of like an average velocity, okay? This is the molar mass of the gas in units of kilograms per mole. It has to be in kilograms per mole because of the other constants, all right? R is the ideal gas law constant, but it's in different units. Okay, so R here is 8.314 joules per mole Kelvin. Notice that this is different than the units we use in the ideal gas law, okay? And your equation sheet has both versions of this constant. You'll have to know when to use which version, okay? Out of all the equations we've seen so far, this is the only one that so far that uses this value of R, all right? And then lastly, T is the temperature in kelvins, okay? So this equation tells us the root mean square velocity of a gas at a given temperature, right? Given that we know the gas is molar mass, right? And notice as the molar mass gets higher, right? As the molar mass gets bigger, what happens to the root mean square velocity? It goes down, right? Why is that? Like we saw, 1/2 mv squared is proportional to temperature. So at a given temperature, a more massive gas, right, is going to have to move slower to have the same kinetic energy as a lighter gas, all right? Okay, let's do an example applying that equation, all right? So we're given here in this problem we're given oxygen gas, right? And we're given the temperature is equal to 25 degrees Celsius, right? And we want to find the root mean square velocity, okay? So we're going to use that equation that I just gave you, URMS is equal to the square root of 3RT over M. Sorry, that's a little funny, but anyway. All right, so we just plug in, right? And we know that the molar mass of oxygen gas, right, is 32.00 grams per mole. But remember, we have to put that in kilograms, right? So in kilograms, that's 32.00 times 10 to the minus 3 kilograms per mole is the molar mass of oxygen in kilograms. Okay. So we plug into here, we get that the root mean square velocity is equal to 3 times 8.314 joules per mole Kelvin, all right, times 298 Kelvin, all right, and we divide by 32.00 times 10 to the minus 3 kilograms per mole. Now, notice that we try to cancel the units out here, right? The moles are going to cancel and the kelvins are canceled, but then we're left with joules over kilograms. So how does that work? Well, the joule is not a fundamental unit. Remember that 1 joule is equal to kilogram meter squared over second squared, right? 1 joule is equal to 1 kilogram meter squared second squared. So if we make that substitution, right, into here, so we're going to take this and substitute it into there, right? We're going to get that the root mean square velocity is equal to the square root of 3 times 8.314 kilogram meter squared second squared times 298 Kelvin over 32.00 times 10 to the minus 3 kilograms per mole. Now notice what happens. Oh, I forgot parens here. Now notice what happens. What I forget? Joules per mole Kelvin. Oh, I forgot some units up here in the numerator. Squeeze them in here. Mole Kelvin. All right. So the kelvins cancel here and here. Right. The moles cancel here and here. Kilograms cancel here and here. Right. And notice what we're left with in terms of units, meters squared over second squared. And when you take the square root of that, of course, you get meters per second. All right. So when you work that out, you get that the root mean square velocity is equal to 482 meters per second. All right? So the oxygen molecules that are in the room around us are moving around at that very, very quick speed on average. Okay. That's their average. That's their average speed at room temperature. Okay. What happens if we change the temperature? Well, this is here we have a graph of root mean square velocity of nitrogen. All right, at different temperatures. And here what I've plotted is not just the root mean square, which is kind of here in near the top, right? But rather the whole distribution of molecular velocities. And you won't have to plot this, but I just want you to see what happens, right? As you take a gas like nitrogen, let's say at 273, right, standard temperature, you see that it has a distribution like this, right? Some molecules, this is the number of molecules, and this is their velocity, right? So most of the molecules, right, a lot of them have velocity close to this, right? Some of them are moving a little bit slower. Some of them are moving a little bit faster, but you see this distribution of velocities, right? If you increase the temperature, right, that distribution moves to higher velocities, right? So now the root mean square velocity is higher, right? But the entire distribution is shifted towards higher velocities. But again, you notice that distribution. Even higher temperature, the whole thing gets shifted even more to higher velocities yet, okay? All right, what about the velocity distribution of gases of different molar masses? Okay, so you already know that at a given temperature, right, all gases have the same kinetic energy. Kinetic energy is proportional only to temperature and nothing else, right? So all gases have a given kinetic energy at a given temperature, all right? But you also notice that the velocity of the gases are not going to be the same for all gases because they don't all have the same mass, right? So we see a distribution of velocities, and that distribution changes for different gases. So here's oxygen, which we just calculated. It's the heaviest of all these, right? As a gas gets lighter, its distribution shifts to higher molecular velocities, right? Again, this is number of particles versus at a particular velocity, right? And so here's oxygen at average this molecular velocity, but as you move over to nitrogen, that average gets higher. Water's higher yet, helium's even higher because it's lighter, and hydrogen is even higher yet. But notice how this also broadens out as you move to lighter gases, okay? All right, here's a question for you. We're not doing polls today, right? Because this isn't live, but you can just pause the video after I read the question to you, answer the question, and see if you're following along, okay? So here's the question. The four most common gases in the atmosphere are nitrogen, oxygen, argon, and carbon dioxide. Which gas has the highest average kinetic energy at room temperature? All right, so pause it now and go ahead and try to answer that question. The correct answer is they all have the same average kinetic energy, right? Remember that kinetic energy is proportional to temperature, and it doesn't matter what the gas is, its kinetic energy at a given temperature is going to be the same, okay? All right, one more question for you. Very similar question. Again, the four most common gases in the atmosphere, nitrogen, oxygen, argon, and carbon dioxide. Now the question asks, which gas has the highest root mean square velocity at room temperature? Go ahead and pause it now and try to answer the question. The correct answer is A, nitrogen, right? Why does it have the highest root mean square velocity at room temperature? Because it's the lightest of all of these, right? It has the lowest molar mass. So if you look at this equation, right? As molar mass goes down, root mean square velocity goes up, okay? Does that make sense? All right, let's move on. Diffusion and effusion. Well, we just calculated, right, that oxygen molecules in the air are moving at 482 meters per second, right? That's pretty fast, right? That's like a football field and a half every second. But why is it that, for example, if I were to open a, let's pretend we were in a classroom here, and if I had a bottle of perfume and I opened it, right? The way we smell those molecules, the way we smell that perfume is that the molecules go from the perfume bottle, which I have in the front of the room, and it gets into your nose, right? It registers in your nose, and that sends a signal to your brain. And you go, ah, that's a nice smell because it's perfume, right? But if I open a bottle of perfume in the front of the room and the molecules are traveling, you know, at 500 meters per second or something like that, why don't you smell it instantly? Well, even though the particles are traveling pretty fast, the path between the perfume bottle and your nose is very, very crowded. Crowded with what? Air molecules, right? Other air molecules. So what happens is that the molecule has to do something called diffusion. It has to move, boom, 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 this random path, right? And it bounces against a lot of other molecules on its path between the perfume bottle and your nose, all right? Nonetheless, the distance it would take, sorry, not the distance it would take, the time it would take to get from the front of the room to your nose does depend on the molar mass of the molecule. So for example, if you had a perfume that had several different molecules in it, right? The lighter molecules would get to your nose first, and the heavier ones would take a little bit longer, right? Because the lighter ones are traveling faster. Why? Because they're lighter, and in order to have the same kinetic energy as the heavier ones, they have to move faster, right? So you'd smell those lighter ones first, and the heavier ones a little bit later. A similar process is called effusion. Effusion is just the escape of a gas through into a vacuum through a small hole, right? And for gases, we can write down what's called Graham's law of effusion, which quantifies this process. So Graham's law of effusion. And this law says that the rate of gas A, the rate at which gas A diffuses, divided by the rate at which gas B diffuses, is equal to the square root of the molar mass of B divided by the molar mass of A. All right? And I want you to note that rate and time are inversely proportional. So if I were to write this for the time it takes for a gas to diffuse, I'd write it as TB over TA is equal to the molar mass of B over the molar mass of A. In other words, the rate is proportional to 1 over the molar mass of the gas, but the time is just proportional to the square root of the molar mass of the gas. Okay? So if you're dealing with times, you use this equation. If you're dealing with rates, use that equation. All right? All right. Let's do an example here. So we want to calculate the molar mass of a gas that diffuses at a rate 0.462 times that of nitrogen. All right. So let's see, what are we given? We're given that we have a gas that diffuses. So we have two gases. We'll call them nitrogen, right? And the unknown gas, right? And we want to find the molar mass of the unknown gas. I want to find the molar mass of the unknown gas. And we're given that the rate of diffusion of the unknown gas is equal to 0.462 times that of nitrogen. Here's where you got to do a little bit of interpretation, right? You got to interpret what that means. So we're going to write it like this. The rate of the unknown gas is equal to 0.462 times the rate of nitrogen gas, right? All right, so so then let's go ahead and write down our Graham's law, right? In terms of these gases, the rate of the unknown gas divided by the rate of nitrogen gas is equal to the molar mass of nitrogen gas divided by the molar mass of the unknown gas, right? Now, what do we know in this equation, right? We know that the rate of the unknown gas is equal to 0.462 times the rate of nitrogen, right? So we know this, right? And we know the molar mass of nitrogen, 28.01 grams per mole. So we know that, right? We're trying to find this, right? That's what we're trying to solve for, all right? So we can start to plug these things in here, right? So we get something that looks like this. Plug this into there, we get 0.462 times the rate of nitrogen over the rate of nitrogen is equal to square root of 28.01 grams per mole divided by the molar mass of the unknown gas, which is the thing we're trying to find, right? Notice that the rates of nitrogen now cancel out, right? So I solve this for the M unknown, right? So how do I do that? I square both sides of the equation because I'm solving for something in the square root, so I square it to get rid of the square root, right? And then I end up, I'm going to bring this over there and bring this over there, right? So the molar mass of the unknown gas is equal to the molar mass of nitrogen, which is 28.01, right? Divided by 0.462, the quantity squared, right? And that comes out to be equal to 131 grams. Okay? All right, that's Graham's law of diffusion. So here's a little question for you just to see if you're getting this. So now this question is asking about time, not rate. So remember that rates are inversely proportional, but times are directly proportional, okay? So you got helium, neon, and argon are mixed in a container with a small hole. Which gas will diffuse in the shortest time? All right, go ahead and pause the video, answer the question. The correct answer to this question is A, helium. Helium will diffuse in the shortest time. Why? Because it has the smallest molar, the lightest molar mass, right? So the lower the molar mass, the faster it's moving, and the quicker, the shorter the time it will be for it to diffuse, right? In terms of the equation, right, the time is directly proportional to the square root of mb. Since it has the smallest molar mass, it has the shortest time. All right. All right. Our last, sorry, no, we already did that. So, okay, so that concludes the material from chapter 6. And so now we're going to transition over to the review for the exam, all right, for the upcoming exam. So exam 2 will cover chapters 4, 5, and 6, all right? So let's just do a quick review of the material in those chapters. So remember from chapter 4, that was the chapter on chemical equations and stoichiometry, right? So we talked about writing and balancing equations. We talked about reaction stoichiometry, right? The relationships, the numerical relationships between the amounts of reactants and products in a chemical reaction. We talked about the concepts of limiting reactant, theoretical yield, and percent yield, right? And then we talked a little bit about combustion reactions. So here are the important skills to know from that chapter. I want you to be able to balance chemical equations, right? So given an unbalanced equation, be able to balance it, or given an equation written out in words, be able to write out the equation and balance it, right? Which means you need to review your nomenclature perhaps a little bit from the previous exam, all right? Be able to perform calculations involving stoichiometry, yeah? So remember, for these kinds of calculations, right, mass to moles to moles to mass, right? And mass to mole conversions are done using the molar mass, right? And the mole to mole conversions are done using the stoichiometric coefficients in the balanced chemical equation, all right? So then the next skill is to be able to look at a chemical reaction with given amounts of reactants and find the limiting reactant, right? And then be able to determine the theoretical yield. And if you're given a yield, the percent yield as well, all right? And then lastly, for this chapter, I expect you to be able to write equations for combustion reactions and recognize those kinds of equations. So remember, combustion reaction is just any reaction in which you react with water, right? So for example, the combustion of carbon with oxygen to form CO2 is a combustion reaction. The reaction with oxygen, then you form the oxide. For hydrocarbons, right, when those combine with oxygen, they form CO2 plus water, right? The hydrogen also gets oxidized, okay? So be able to write balance equations for combustion reactions and be able to recognize them. All right, what do you need to know in terms of equations for chapter 4? Not a lot of equations here, but a lot of mathematical calculations, of course, for stoichiometry. Remember, of course, mass to moles to moles to mass. We'll be doing that a lot, right? And then the percent yield equation, which is this one. Okay, chapter 5. So chapter 5 was the chapter on solutions, right? And reactions in solutions. So we started out talking about solution concentration, right? So be able to calculate molarity Be able to use molarity as a conversion factor, right, between moles and liters, or from liters to moles. We talked about solution stoichiometry, right? So here, instead of mass to moles to moles to mass, you might have volume of the solution, right? And if you have the molarity, you can go to moles, and then back to volume or whatever else it asks, right? We talked about the different types of aqueous solutions, such as electrolyte, non-electrolyte, weak electrolyte, acids, strong acids, weak acids, right? All those different solution types. So make sure you know those. We talked about the solubility rules, which tells us whether or not a particular ionic compound is soluble in water. So you need to know those for the exam. Precipitation reactions. Be able to recognize when a precipitation reaction will occur, right? And be able to write a balanced chemical equation for a precipitation reaction. Be able to write molecular, ionic, and net ionic equations for precipitation reactions, as well as the other types of reactions in this chapter, all right? Acid-base reactions. So remember, acid plus base forms water and salt. Gas evolution reactions. These are the reactions in which two reactants mix that are aqueous and they form a gas that bubbles out, right? And there's certain things to look for there in terms of what can form and what kind of gases form as a result. And then lastly, we talked about oxidation states, be able to assign oxidation states to elements in a compound, and be able to recognize oxidation reduction reactions, be able to identify what's being oxidized and what's being reduced, and be able to identify the oxidizing agent and the reducing agent. Here's a list of skills for this chapter, right? Calculate molarity, apply it to conversion and dilution. Calculate the amounts of reactants and products involved in aqueous reactions, right? So basically reaction stoichiometry in solution. Know the solubility rules and be able to classify compounds as soluble and insoluble, electrolyte or non-electrolyte. Be able to write chemical equations for precipitation reactions between two or more aqueous solutions. Be able to write the molecular equation, complete ionic equation, and net ionic equation for all these types of reactions. Be able to write molecular, complete ionic, and net ionic equations for neutralization reactions. That's acid-base reactions, right? Acid, base, water, salt. Actually, this one we're not doing on the exam. You did some of this in the lab, but this will not be on the exam. You will not have to perform calculations involving titrations for the exam, okay? So I should have crossed that out. I forgot to, but this will not be on the exam. Be able to write equations for gas evolution reactions. Be able to determine the oxidation state of elements and compounds, and then determine if a reaction is a redox reaction, and if so, identify the oxidizing and reducing agents. Okay. Chapter 5, equations, right? The equation for molarity. So know that and know how to use that. Solution dilution, M1B1 is equal to M2V2. And then solution stoichiometry, right? Volume A, amount B, volume B. All right, moving on to chapter 6. The concepts in chapter 6 were pressure. So we talked about pressure, so know what pressure is and be comfortable with the units of pressure, right? Know each of the simple gas laws and how to apply them. Know the ideal gas law and how to apply it, right? And specifically know how to apply it to the density of a gas, to the molar volume of a gas. Remember too, a handy thing to know is 1 mole is equal to 22.4 liters at STP, all right? That comes from figuring out the molar volume of a gas at standard temperature and pressure, right? Which is 1 atmosphere and 273 Kelvin. And then know how to apply the ideal gas law to find the molar mass of a gas. Mixtures and partial pressure, so know how to deal with mixtures of gases and know what partial pressure is and how to work with that. Then gas stoichiometry, so Notice for regular stoichiometry, we had this. For solution stoichiometry, we had that. For gas stoichiometry, you can go from volume of a gas, and then you use the ideal gas law to get to moles, to whatever you need to get to, right? Same, very, very similar pattern in all three of these. And then lastly, we talked about kinetic molecular theory, specifically know the assumptions of kinetic molecular theory and know how to calculate the root mean square velocity of a gas and know how to work with Graham's law of diffusion. All right, chapter 6, key skills. Be able to convert between the different units of pressure. Be able to calculate properties of gases using the simple gas laws. And then be able to calculate properties of gases using the ideal gas law. Be able to analyze gas mixtures using Dalton's law of partial pressure, right? And then be able to do stoichiometry for gas reactions. Be able to calculate the root mean square velocity of a gas. And then lastly, be able to apply Graham's law to calculate the effusion rate of a gas or the ratio of effusion rates of two different gases. All right, this chapter does have quite a few equations. Pressure is equal to force over area. That's a definition of pressure. You really won't have to use this equation in any calculations, but you should know the concept here, right? It's force per unit area. Know Boyle's law, Charles's law, and Avogadro's law. And then, of course, the ideal gas law, PV is equal to nRT, right? Know Dalton's law of partial pressure, right? The total pressure is equal to the sum of the partial pressures of the components. And then that any individual gas, right, you can get the partial pressure of that component if you know the mole, the number of moles of that component times RT over V. Know also the definition of mole fraction. The mole fraction of a component A is equal to the moles of A over the total number of moles. And the partial pressure of A is equal to the mole fraction of A divided by the total pressure. So if you have 1 atmosphere of total pressure and you have a mixture that has equal number of moles of two gases, right, then each gas, right, has a partial pressure that's half of the total pressure. The average kinetic energy, according to kinetic molecular theory, is 3/2 RT. Again, this is just, you just need to know this in concept. You don't have to apply it. Just the important thing here is that as temperature goes up, the average kinetic energy goes up, right? Root mean square velocity, here's the equation for that. Root mean square velocity is equal to the square root of 3RT over the molar mass of the gas. Be able to apply that. And then lastly, Graham's law of diffusion, rate A over rate B is equal to square root of molar mass B over molar mass A. Remember, if these are times instead of rates, then the proportionality is direct instead of inversely proportional, okay? All right, and that's it. That's all the material that'll be on the exam. Again, remember the exam is gonna be on Thursday from 2 to 11. It's gonna be 80 minutes long. I'll send you an email, another email reminding you of those details. And if you have any questions for me from this lecture, you can always email me, or I'll be available on Tuesday during my office hour time. Send me an email to schedule something. And then Wednesday from 1 to 2, I'll be on Zoom, and you can come in and ask any questions you would like at that time. And then the exam is on Thursday. Okay. Thank you all. I hope you have a great day, and we'll see you soon. Bye.